when we go to the reinforcement learning. And then I was actually kind of toying between that and statistical learning as the next chapter, next topic, but I think after reinforcement learning we'll get to statistical learning, which would be sort of, so basically the rest of the semester would be sort of learning oriented. Okay, any questions? I also sent a note to you guys saying that there would be, that you would have to put up your progress reports on your projects on the same wiki page. Okay. So last time we were talking about the value iteration for POM-DPs, and basically, if you remember, what we were doing was we were considering this is again a quick review. So if you take something, a very simple POM-DP here, where you have just two states and you have only two actions, and you have a noisy observation where the sensor reports the correct state with 0.6 probability, and the way, and if you're trying to compute the finite horizon policy, then you first compute the finite horizon value function and then use that to compute, get the best action. Okay, and if you have one, if the horizon is 1, then basically you only get to do one action, and so what you will wind up doing is compute what are called the alpha vectors. In POM-DP value iteration, the big issue is the alpha vectors for a plan. Okay, an alpha vector for a plan is the expected value you can get for that plan from each of the pure states. And a belief state is just essentially a distribution, so it's sort of a distribution over the pure states, and so the expected value in a belief state would be some linear function. It's like some dot product of this alpha vector times the belief state. Okay, so one of the big deals that we'll talk about is the number of alpha vectors. By the way, I mentioned before I came to I sent this morning a paper in JAIR on online POM-DPs. That's this paper. I sent you a link to it. I know that you wouldn't have been able to even open it by now, but the online part, as well as a quick overview of a whole bunch of other approaches to POM-DPs, are provided in that paper. So you can sort of look at that to get a feel for where the area is right now. Okay. So you mostly, what we are doing is we're going to just understand value iteration, but then we'll skip over to approximate methods. But that particular paper has all the methods, at least, it focuses on the online methods, but it actually also has background on some of the offline methods. The difference between offline and online is, in the case of offline, you compute the full policy and you just start executing it. In the case of online, you essentially take part of the time you have to figure out what action to do from the current belief state. Do it, observe what you got into, and then move on. Okay. So in this particular case, we looked at the alpha values for, there are only two plans. If you only have horizon 1, there are only two plans, because there are only two actions. You can either do action 1 or action 2. And so for each action, you compute the alpha vector, which would be as long as the number of states. So you're computing what's the value of staying, what's the value of doing the stay action starting from 0 state and starting from state 1. And similarly, go action from 0 and 1. And then you get these rewards. Okay? And then, so what you basically, and then when you actually multiply this is basically a two-state problem. So essentially, the alpha times this particular thing is actually showing you the probability of state 1. So 1 minus that would be the probability of state 2. And so you can actually look at the the alpha vectors actually will have the values, so which is the one, this is 0.1 and 1.9, that's the state 1, and then this is the go 1, and then both of them in between those 2 points, it will just be a hyperplane. Since it's a, it's a one-dimensional case, in this case you get a line. Okay, normally you get hyperplanes, and you're guaranteed that this thing will be convex, because having less, you cannot do worse than, you cannot do worse in all the pure states than any belief state. So if you consider all the belief states that correspond to the pure states, one of those better have a better valuation for your plan than any which actually combine a couple of those states. Do you understand what I'm saying? Okay.
So 0 and 1 are pure states.
Yes. Now in this particular case, 0 means the probability of state 1 is 0, that means you are in state 2. And the probability of state 1 is 1, that means you are completely in state 1, you're not in state 2. And in between you are, partially in both states, according to your belief. Okay, so you got these the hyperplane, and then since you get to choose the best value at every point, if you are in a particular belief state, let's say here, then you will realize that by doing this plan you get this much value, by doing this plan you get this much value, so you will pick the higher one. So in general, the upper envelope essentially gives you the value function. Okay, and that much is for sure. And now basically now I have the value function for horizon 1. This is what you're going to use in computing the value function for horizon 2. Now horizon 2 itself will have horizon 2 sized plans. The interesting thing, of course, is as the horizon increases, the number of plans increases exponentially. Here you just had 2, and in this particular case you had a scenario, a very simple scenario, right? So you have 2 observations, so you can still, so you have, a horizon 2 plan would do an action, and then based on the observation do another action. Since there are 2 observations, so there will be trees of size, trees of branching 2. Okay, and you could have 1 of 2 actions here, 1 of 2 actions here, 1 of 2 actions here. Right? So there are 8 conditional plans, okay, for horizon 2. And by the time you get to 3, then it will be, increasing again exponentially. Okay, so that's basically, and so when you have these conditional plans, you can compute their valuation. For those 2, you are computing the alpha values. That means if you do this conditional plan in a pure state, what is the value you get? Okay, and that would be in terms of, and so the alpha value in a pure state depends on the alpha value of the sub-plan in the neighboring pure states, which you have computed in the previous iteration. Okay, so alpha p of s is in terms of alpha p dot e of s dash, which you computed in the previous iteration. Okay, so that's basically the idea of value iteration. Okay, and it looks easy enough in terms of each step, but the problem is, first of all, there are huge number of these plans. But as the iterations increase, the number of plans are going to increase significantly, and most of them are dominated. In the worst case, a whole bunch of them are non-dominated, and the question, of course, is you're wasting all the time, generating all of these and then computing the upper envelope. Okay. Just to give you an idea, the number of alpha vectors needed at the tth iteration would be of the order of the number of alpha vectors required in the t minus 1th iteration, because remember the t minus 1th iteration plans become the sub-plans. Okay, when you increase the iteration, you put an action on top, and then consider all the observations. And after that observation, you will do one of the previous iteration plans. And so in general, basically this in itself could be a conditional plan. And so you have, A times the number of alpha vectors from the previous iteration power Z. Why? Because the reason for power Z is the Z is the number of observations. Okay? Under each observation you have a branch which you can fill to your heart's content with any of the t-1 plans. Which is why it's tau t-1 power Z. Okay? That's for the bottom part, and in the top part you can have any of the actions as the root. So that is A times t tau minus 1, tau t minus 1 power Z. Okay, that's your number of alpha vectors. Okay, and then time to compute each alpha vector. Computing the alpha vector means computing these numbers. Okay, so that basically is in time proportional to the number of actions and the number of states. Actually, it is AS square, I believe. Yeah, I'm sorry. It's number of. So this is your computation of alpha vector. It should be in terms of. It's not in terms of number of actions, obviously. If you're doing it one for each of the actions. It has to be in terms of number of states and the observations. Okay? And so, it's number of observations times state square. That's the total amount per alpha vector. Which basically means this is the complexity for one iteration of PAM-DP value iteration. Okay, so it's like ridiculously complex procedure. Okay, and so obviously while you can pat your back saying that we now have a value iteration algorithm that actually converges, it's also extremely hard. Okay, and it's not surprising that these are all exponentials, because we already know that for finite horizon case the complexity of PAM-DP value iteration, PAM-DP policy computation is p-space hard. Okay. Okay. So this is the amount that you're spending per iteration. So clearly you are interested in reducing that complexity, and you want to do various approximations. Okay. Before I start talking a little bit about approximations, let me also say that one other part that I'm completely not talking about here, but mostly telling you that it's out there, is just as MDPs have value and policy iteration, PAM-DPs also have value and policy iteration. Okay, if you are interested in the policy iteration, then essentially what you wind up doing is you essentially consider plans which are certain finite state controllers. Okay, so where the controller itself has an internal state, and based on its internal state and the observation it gets, it does an action. Okay, and so you basically will search in the space directly of the controllers. Okay, this is sort of almost like partial order planning, where you search directly in the space of plans. You see what I'm saying? And there are approaches for this. In fact, I think Hansen's method, Eric Hansen and co have done some work, and there's some more recent work going on Mealy machines. Basically the representation of what differentiates one of these from the other ones is the representation used for the plan. Okay, and clearly the plan needs to have an internal state. There is actually a direct policy iteration, analog of a direct policy iteration like from the MDP case, but that turns out to be just impossible even to do one iteration. Okay, so much of what happens in these cases is at least get me one iteration before I die, right? I mean, then so that's, and in this case, by looking at plans of a certain restriction, expressiveness restriction, you might be able to consider what's the best among those plans that corresponds to the optimal policy. So which of them is optimal for this? That may not be the globally optimal policy. Okay. Okay, so this is basically to show, I mean, there is no technical content here other than showing that you start with a small plan and then you tweak the plan and consider what is its effect on the value function and then look for the best tweak, essentially. Okay, so that's the kind of thing that happens in the policy improvement algorithms. But those are also offline. That means they compute the policy upfront. Okay, so you can have online versus offline. And then in the offline you can do value iteration, and then once you have the value you can compute what the optimal action is. Or you can do policy iteration, which is this. Okay, and value versus policy iteration, by the way, really is like state versus plan space search. State space versus plan space search in our planning terminology. Those are sort of analogous. Okay. Finally, those are both offline ones. The other thing is that, so since if you start with the value iteration, since each iteration is extremely hard, you want to consider what are the approximations. Okay, so suppose you want to do offline, but you want to approximate the value function. Okay, what could you do? The interesting thing, of course, is POMDP is at the top of the complexity of the models we have seen till now. Okay, so you have deterministic planning, which could be relaxed in only a few ways. You could relax the negative interactions. You can relax the positive as well as negative interactions. Okay, those are the relaxations that you could do. Then you went to MDP, which is basically stochastic planning. There you could relax the stochastic outcomes, and then you can also relax the positive and negative interactions. So more relaxations. Now you finally come here, you get to also relax everything that we relaxed before, plus more. Now you can relax partial observability. You see what I'm saying? Actually, in terms of relaxing partial observability, actually, we will talk about one relaxation method. We can also talk about over-constraining it. So in the case of partial observability, it's like you can barely see, right? So one idea is to truly relax it and say everything can be seen. That would be a fully observable case. Okay, so if I take a POMDP and assume full observability, then basically I am searching in the space of states directly, not in the space of belief states anymore. Okay, yes?
If you do that, you essentially have a co-MDP, right?
What do you mean co-MDP?
Fully observable Markov decision processes.
FOMDP, yeah. Yeah, FOMDP. Yeah, fully observable Markov decision process. So basically, when you are partially observable, you can either relax and say the world is much, much nicer than I expected, what I'm given, so I can actually see everything. So fully observable Markov decision process. Okay, now when we were in MDPs, the thing about relaxations is that day before yesterday's hard problem becomes today's subroutine. Right? When we were in deterministic planning, we hated deterministic planning. We needed to relax it by relaxing negative interactions, etc., etc. By the time we came to stochastic planning, deterministic planning was our friend because we could use that as a subroutine as a relaxation of the stochastic planning. And then basically when we come here, when we relax it to FOMDP, then that is all the stuff that we did a couple of weeks back. How, FOMDPs aren't exactly that easy. They're polynomial in the number of states, which means they're still exponential in the number of literals. Okay, it's just that polynomial in the number of states looks very nice compared to p-space hard in the number of states. Right? So when you relax it to FOMDP, then basically all you need to do is just run FOMDP value iteration algorithm, which is only polynomial, in the number of states. And you will get the optimal value. And then basically that will give you the valuation for individual states. But clearly you will still not know, just because you acted as if your world is fully observable, it hasn't suddenly become fully observable. Okay, all you would now know is if you for each real state of the world, you know the optimal value if the world was fully observable. But you actually, at any point of time, you, the agent, will realize that you are in some belief state B. Okay, which gives some probability for each state. Okay, so if I were to compute VMDP of each state, then I multiply that by B times S, sum over S. That will give me the expected value of my belief state. Do you see what I'm saying? It's not the optimal value whatsoever. It is, a reasonable way of taking this approximation that I have, which is for each state, and making it mean something for the belief state. Yes, sir.
It seems like it won't always give the optimal value though, because
it doesn't give optimal value at all.
well, I mean, it seems like it won't give you the expected value because when you relax to an MVP, it's not just the initial state that you're assuming is fully observable, but after you perform an action, you know exactly where you end up.
Yeah. No. You after you perform that, so all you do essentially when you take a PALM DP and convert it to in fact, it's a worthwhile thing to look at our formal model of PALM DP, which may be somewhere. Where is my? Yeah. Okay, right? So this is the PALM DP. When I'm relaxing, I'm only relaxing one little thing. I'm just changing the observation function. So observation function basically gives me the state value directly. That's what I'm assuming. Okay. So it will be 1 for the state you currently are in and 0 for everything else. In which case this really becomes a PALM DP. And then you can compute the optimal value. Then later on, somebody tells you, basically imagine the following thing, right? Suppose you are in a fully observable Markov-Adation process and you computed the values of each of the states. Okay, then your friend then sort of played this game with you. They said, close your eyes. Before opening your eyes, I'm telling you that you are S1 with 50% probability, S2 with 50% probability. What do you think is your value? Since you know that overall value of S1, overall value of S2, then it's, half plus half of those would be the expected value you have. Now, this basically made sense in that scenario because once you actually start executing, you do see your states. Whereas in the PALM DP scenario, it will never really make sense, because after you figure out the value of your belief state, even when you open your eyes, you still only have the belief state. You will never really see the state. So it is a true approximation. The question, of course, is okay. So the question, of course, is that is this value of the PALM DP, is this going to be upper or lower bound? It's going to be some sort of an approximation, right? Is it at all connected to be either upper or lower bound of the true value for the PALM DP? What? It should be an upper bound on the value or lower bound on the cost. Right? Remember, you can have one other thing that I won't go through here, but it sort of follows is, remember, after the MDP, normal discounted MDP model based on values, we also considered a whole bunch of other MDP models, the cost-based models, non-discounted versus discounted, etc. Okay, cost and value are basically opposites of each other. So if this is an upper bound on the value, it will be a lower bound on the cost. If it's lower bound on the cost, then we are happy because it can be seen as a heuristic and it will be an admissible heuristic. Which is not surprising because you are relaxing it, and if you found the optimal policy for PALM DP, then it will be a lower bound heuristic. If you don't find the optimal policy, then it's like optimal relaxed plan is a lower bound heuristic on the real plan. Okay, but if you just find a greedy relaxed plan, it may not be. So here we'll act as if we are computing optimal, in which case it will be a, it will be a optimistic bound on the value. That means it's going to be a principal heuristic. Okay, so you essentially assume the world is easier than it is, which is normal, which is the way you get lower bounds. I mean, upper bounds on the value or lower bounds on the cost. Okay, you just should not get confused on that. Okay. The other thing, because it is about the observability, right? Because it's about the observability, you could also essentially constrain it to be non-observable. That's not relaxation. That's not relaxation. That's like, you basically are having trouble looking at the world, it's all bloody, so you just poke your two eyes out. At least you are now blind. So people cannot complain that you are not doing things right. Okay, I can't see, so you should not yell at me. Okay, and we talked about this because NOM-DPs are actually easier than POM-DPs. They have it easy because they can't actually compute, they can't actually achieve all the goals. By the way, that's the other issue. We looked at the POM-DP model for value rather than cost, discounted, and we also considered non-goal based, sort of, because rewards, every state has reward, no state has to be essentially a sync state. Okay, but you also can actually consider goal based POM-DPs. So those are all still possible. This is just a general discussion for one model. Okay. If you remove full observability, if you remove all the observability, then essentially you have conformant planning. Okay, and this is, again, this should not be too surprising to you because when we left non-deterministic conditional planning, I said if you have conditional plans, you can use conformant plans as a heuristic. It's not a good heuristic, it will actually be an overbound, not an upper bound, not a lower. It will overestimate the cost, it won't underestimate the cost. Right, because a conformant plan basically sees much less, so if you can reach the goal without opening your eyes in 10 units cost, then you cannot, the optimal plan with opening eyes cannot be costlier than 10 units. It has to be lower cost. Right, because in the worst case you can just decide not to take the observation. Okay. In fact, NOM-DP policies are really just one of the policies that, a NOM-DP policy is a legitimate POM-DP policy. Right? Because, remember, what is a POM-DP policy? Take the belief state, tell me what the action is. A NOM-DP policy says, give me the belief state, I throw it out, I'll tell you what the action is. Do you see what I'm saying? And that's still a function on the belief state. It just ignores the belief state. It's a constant function. Okay, now then the interesting question of course is it a finite or infinite horizon? If it's a finite horizon NOM-DP, then you give both the belief state and the horizon, remaining horizon. And then it throws the belief state out, just looks at the horizon and says, do this action. That means first action is this, second action is this, third action is this, fourth action is this. That's finite horizon NOM-DP policy. If you only have one more iteration to live, then do this action. If you have two more iterations to live, do this action. If you have three more, do this action. It doesn't matter what your belief state is because you don't get to open your eyes. Okay, that's your NOM-DP policy. Now, if it is infinite horizon, NOM-DP, then life becomes even simpler. Because there is no such thing as the last stage. You always have infinite amount of time to live. So you really can't say, if it's infinity minus 1, do this action, infinity minus 2, do this action. So essentially, for an infinite horizon NOM-DP, the number of policies are exactly A, where A is the number of actions. Because always do A, or always do B, or always do C, or always do whatever, if there are A number of actions, 10 actions, then you have 10 policies for NOM-DP. If you have 10 actions and you have a finite horizon, then you get to do A power the horizon, which is something that we talked about. The number of policies for a finite horizon case is, lot more than the one for infinite horizon case. Okay, so anyway, the interesting thing is now in this case, I did not actually tell you how to compute this policy, but it turns out that since there are only A policies, it shouldn't be hard. Especially for the infinite horizon case, there are only A policies, A being the number of actions. And it turns out it's actually quite easy to compute the value function corresponding to not ever opening your eyes. Now, that value function would be what? Would it be an upper or lower bound? Over the value, it will be a lower bound. Over the cost, it will be an upper bound. Okay, so it's kind of, I gave you two approximations for instead of the real thing. This one is an upper bound on the value, this is a lower bound on the value. Or this one is the lower bound on the cost, and this is the upper bound on the cost. Okay, and so this one underestimates the value, so it overestimates the cost. And this one overestimates the value, that means underestimates the cost. Okay, this stuff you know how to do because we already completed it. This one I didn't actually discuss, but there's a little section which tells you, how to do non-DP case, because they only, for especially infinite horizon case, there are only 8 different policies. And you can talk about what, which of them is the best, yes?
So in principle, FOMDP is of lesser complexity than a non-DP.
FOMDP is higher complexity than non-DP. NOM-DP is NP complete, POMDP is P-space complete for finite horizon. FOMDP is polynomial. And these are all in number of states. No, right? And okay. Okay. Now, having said this, so these are actually useful to have because as your problem becomes harder, cynically speaking, you have more ways of relaxing it, right? I mean, when you are deterministic planning problem, all you could relax was the interactions, positive and negative interactions. And then you did the uncertainties, now you get to relax the observations. And so the cottage industry of approaches grows also exponentially. Right, because you can take this and this and this, you have an approach. And it's a different relaxation from this and this and that. Okay. The other thing, of course, is that, so now, of course, I mean, to make yourself, when you relax FOMDP into a FOMDP, you can then relax the FOMDP into some deterministic, the kind of approaches we talked last time, approximation approaches for FOMDPs. Those could be used to compute these too. And so there are stacked amount of approximations going on. And that becomes obvious in the next iteration, next slide. But here's a good thing to keep in mind, which is that, since we gotten into the approximations, because even per iteration complexity of value iteration for FOMDPs is so humongously expensive, because the number of alpha vectors you have to consider is just, increasing exponentially in the number of observations. Right? Okay? But if it is fully observable, or if it is not at all observable, then the per iteration cost will be AS square. In this case, it will be AS square because there are only alpha, which is the number of vectors, is only A, because the only number of actions are A. Number of policies, number of different policies are A, and so it will still be A square. And this one is because that's the way FOMDP is working. Okay, so that's per iteration is lower, and you could use this as an offline scenario. So up front, you just go ahead and compute the offline upper and lower bounds for values and just stop. You could do that. Or you could actually combine this into an online scenario, okay, which is the last part of this FOMDP discussion I want to make, which is sort of like what FF-hop was doing. Remember, FF-hop basically did online decision making. It started from the current state, considered the actions it can do, and then computed for each of those actions what is the expected value of them by looking some fixed look ahead, some finite look ahead, and then decided which action to pick. Right? So The same thing can be done here, except the picture looks slightly more different. It obviously looks different. Okay. So first of all, so here is a picture that we should try and understand. So here you start from the initial belief state. Again, think of this as sort of a RTDP tree or the min-max tree, except you're just playing against nature in this case. Playing against nature and your bad eyesight. That's what you're playing against right now. Okay. So you started with the belief state. Okay, and those numbers for the belief state next to the belief state are the backed up essentially upper and lower bounds. And so they're kind of like, if you remember your min-max search, what are they like? Alpha beta bounds. Okay, except unlike alpha beta where you actually get the true values for the leaf nodes and then you get upper and lower bounds while backing up because of mins and maxes. Here you actually wind up for the leaf nodes, you will assume that you would have computed these two already, upper and lower bound valuations. And so for each leaf node you will actually give its upper bound value and the lower bound value based on the form DP and norm DP relaxation. And then these upper and lower bounds are propagated up the tree. Okay, now first you have to construct the tree, stop somewhere, apply the quote-unquote heuristic values, in this case both upper and lower bound heuristics, and then you back it up. Okay, and then the paper that you are looking at, essentially this picture is actually from that paper, and this paper talks about many different variations on how to grow this tree and how to evaluate the leaf nodes. Okay, so for example, you can grow it in such a way that they're all fixed depth everywhere, or you can grow it in such a way that the nodes that are most likely to change your overall action are going to be grown further. Okay, and similarly for the heuristics, you can do just one approximation or both upper and lower bound approximations. And so you get like a whole bunch of different, online POMDP approaches. And so they sort of try to do some comparison between them too. Okay, the other thing that's kind of worth understanding here is, so in this picture, essentially, you started from the belief state and you did this action A. There are only two actions in this case apparently. So you did action A1 here and A2 here. Okay, that's an R choice. It's an R choice. Okay, and if you do A1 basically in B0, the cost or the value is 1, and the reward basically is 1. And if you do A2 in B0, the reward is 3. That's the immediate reward. And we are talking right now in the value language, but you can do the whole thing in the cost language too, in which case you will be talking about cost of the actions and the cost of the final states. Okay, except these states are not real world states, but they are belief states. Okay, so now, so you're in B0 and you considered two actions A1 and A2. Now one of the interesting things is, given just the model and nothing else, you would know these numbers, right? Because the reward model is known. You know how much reward you're going to get when you do an action in a state, and you also, given a belief state and do an action, you can compute the next belief state. And that's that formula. Okay, so basically that next belief state is nothing but, for each action there is a deterministic transition model. There's a full observable transition model, which basically says, if you were to do this action in S dash, what's the probability that you will get to S? Times the probability that you are in S dash to begin with, according to your initial belief state. And you sum this over all S dash, then you will get the total probability of getting to state S after action A. Right? This basically is telling you that you could be in S0 or S5, and if you are in S0 and you do this action A with 0.1 probability, you will get to S2. If you are in S5 and you do this action A with 0.3 probability, you will get to S2. Okay, and if you assume that in the previous case you assume this S0 and S5 with 0.5, 0.5, then it's 0.5 times the first probability plus 0.5 times the second probability is the probability of being in S2 after this action. Okay, so that's, you can compute that, right, because it's just directly available. This part is available from the action transition model, so you can compute the new belief state. Okay, now once you compute the new belief state, when you get the observation, that actually changes the belief state distribution again. Right, because the states that are consistent with the observation will get more probability and those less consistent will get less probability. Now, this part, where was this part in the non-deterministic case? So basically, after this action, after that, if in this case I'm considering observation Z1, and this case I'm considering observation Z2. Okay, if I get Z1, then I will be in B1. If I get Z2, then I will be in B2. Okay, those two belief states are drawn from this belief state. Right? So this actually, even though both of these are belief state distributions, they really, what they did was they changed the original belief state. I mean, the one that you remember from the non-deterministic case is if you were in a non-deterministic belief state and you did an observation action, what happens? What happens? What? What? Yeah, basically the belief state, suppose you are in S1, S2, S3 and you did an observe P. Okay, so this is true, P true, and this is P false. And these, let's say, have P true, here it will be S1, S2, this, let's say, is P false, this is S3. So in the case of non-deterministic scenario, non-deterministic one also had this other additional thing, because we don't talk about probabilities in the non-deterministic case. So the observation has to be categorical observation. You cannot talk about noisy observations in the non-deterministic scenario. So if you have categorical observations, belief states just get split, they get partitioned. Whereas if you have noisy observations, so in some sense you should think of this is 1/3, 1/3, 1/3. In a weird way of thinking about it, you can say this is 1/3, 1/3, 1/3 belief state, and then it became a half and a half belief state here. So it's basically half, half, 0 belief state here, and 0, 0, 1 belief state here. That's what you did. If you actually have probabilities, you will then compute using the Bayes rule the exact distributions after the observation. Right? And that's basically what you're doing here. And notice there is a division, that's Bayes rule division. Okay? And then finally, one of the interesting things is in the non-deterministic case, when I say observe P, I have no way of telling upfront whether I am likely to get this observation or this observation. Well, actually I kind of can, right? Well, I mean...
You can guess.
No, okay, here's the interesting thing. Because I wrote it like this, 1/3, 1/3, 1/3, it looks like I should know that this observation is going to occur with 2/3 probability, and this will occur with 1/3 probability. You agree? Right? Because if you have only 3 states, 2 of them have P true, 1 has P false, then when you actually observe for P, if you are equally likely to be in all these states, then you should have 2/3 probability for this branch, 1/3 probability for this branch. This was your prior estimate as to what you will observe. Okay? But non-determinism is not uniform probability. Although we once in a while just act as if it is, non-determinism is not uniform probability. It basically means I have no clue what the distribution really is. So because I don't know what the distribution really is, in fact this could be 1, 0, 0, or 1, 0, 1, 0, or 0, 0, 1, and so these probabilities can be anything. So in a true non-deterministic case, before you make an observation, you have no prior belief as to what that observation will wind up as. Do you see what I'm saying? Whereas the moment you have distributions attached, so for example, 1/3, 1/3, 1/3 would have been a not have been a non-deterministic case, it would have been a stochastic case. In that case, I know this is 2/3 probability, this is 1/3 probability. Okay, so I am primed to believe that this is 2/3 probability, this is 1/3 probability. Now if I actually get this, then what happens? I'll go change my mind as to where I was before. Do you understand what I'm saying? It's just beautiful. I mean, you know, the reason people sink into POMDPs and never see the light of the day again, because each iteration itself is exponential, is because it's a beautiful model. It contains, you know, pretty much all the complexities you could think of, you know, and so essentially this idea that based on this observation you can go back and change where you were, that's smoothing, right? Based on the future observations, you change your view as to where you were to begin with. If you are an agent, you're currently most interested in knowing where the heck you are right now. But if you also want to kind of do some introspection, right, and want to know, did I actually run over a log or a person when in the night there was a dull thud, you know, when I was driving, right? And then you come home and you find a huge amount of blood marks and you realize there are very few trees which will give blood marks on the car. And so you changed your belief state as to who you ran over the day before. Right? Which is something that you could not have done. I mean, nothing could have actually changed, particularly in the context of non-deterministic scenario. Okay, it will change because, you know, non-deterministic scenario, you never had any distribution associated with S1, S2, S3 at all. Okay, so just a second. So each branch has a probability associated with it, and that basically again can be computed directly. Because you know after you do A in B0, you get BA, which is the expected belief state. So what really happened is that you could think of it this way. So you were in some belief state and you did A and you computed that you are in this belief state now. Then you did this observation and you could be, after the observation you will know that you are in this belief state or this belief state. But before the observation, you won't know which one you are in, and so there is a probability that you go here, the probability you go here, and they'll add up to 1. And you are supposed to deal with both those possibilities up front. Right? And that is basically what's being done here. This is a 0.7 probability that you will actually get this observation. This is a 0.3 probability that you will get this observation. This is at the planning time, because at the planning time you will never really know what actually happened. This is your expectations. Okay, one very interesting question is in these partial observability scenarios is where you get to talk about value of information. Okay, so the value of information is it worth testing to see some particular before I continue planning, is it worth testing to see that a particular observation actually holds in the current world? Now, if according to my own belief this is 1.0, this is 0.0, is it worth testing it then? Not really. If it's 0.5, is it worth testing it? Yes. But it depends on whether the values of the states you get into based on the observation are quite different. If they are very similar, then again I don't care. So the value of information depends on the probability times the value you will get on both directions, and then the differential between that. Okay. Anyway, we can talk about it some other time, but that's another interesting point, because when partial observability, even before you open your eyes, you know what to expect based on your internal model. And then when you open your eyes, the world tells you what really happened. Okay? So anyway, so you then basically, if you come this side, you will be in B1, if you come this side, you will be in B2. This is like in conditional planning in not deterministic scenarios. If you went this side, this will be in S1, S2, otherwise you will be in S3. And you have to take this to the goal, this to the goal. The same thing here too. Right? Okay? So then you will finally, when you get to B1, then you can again consider the actions you can do in B1, you can consider actions you can do in B2, and so on. The cost of expanding a node is essentially computing the internal belief state and computing these probabilities. That's the cost of expansion. Okay? And then finally, when you get to a leaf node, if you stop expanding, then you need a values for the leaf nodes. Right? And the values for the leaf nodes, if I tell you not, if I, by default, based on our previous description here, I could upfront have computed a normDP and a formDP value function for this, in which case I would know the upper and lower bounds, lower and upper bounds for all the values, all the nodes. Okay, and then you essentially take the lower bound. So this is 6 times 0.6 plus 9 times 0.4 will become the one for the lower bound for this, right? And then similarly 14 times 0.6 times 12 times 0.4 will become the lower bound for this, upper bound for this. Okay, and then similarly when I go here, I basically, I'm getting a value and I can subtract that, I can add the reward and then take it further. So those are what are being shown here. Okay, there's upper and lower bounds are there for the leaf nodes, and then the parent nodes will get their upper and lower bounds based on the leaf node upper and lower bounds. Okay, and then of course based on this, just like so if you only have one bound, then based on what you got, you can decide which action is likely to be more interesting. Okay, so for example, in this particular case, actually, it turned out bad. So this life hasn't been fair to us in this case. In this case, if I stop here, right, according to the upper bounds, this is a good guy. Right? These are all the backed up values. The values in the square brackets are all the backed up values, just like in min-max search. According to the upper bounds, this is a good guy, so I would have just taken this. According to the lower bounds, actually, this is a better guy. Right? And so, you can then, at this point, you can always just do some random thing. For example, you can always say, take the average, and whichever is having a better average, I'll take it. But having the bounds will also help you decide whether or not certain things should even be worthwhile expanding. Right? If, for example, this one is 14.4 and 17.9, and this one is 12 and 16, then there is no point in expanding this any further. Right? Because it's kind of subsumed by the other guy. And this is sort of like the alpha beta pruning that's going on here too. So you can do pruning. And so they talk about a branch and prune approach for doing this kind of online decision making. Okay, the nice thing about this is you're not talking about alpha hyperplanes, you're not talking about, everything is actually just rolled into this picture. You're doing them, except you're doing them piece by piece by piece. Basically, you unroll it to a certain level and then back it up. Okay, and the full analysis you did, you are only doing it for the norm-DP and form-DP approximations at the bottom. That's not necessarily the only ones. You could do it pretty much any heuristic value for the belief states and the leaf level. And then you take it up. Okay, so this is a way in which you can do, and then once you decide to do an action, one of the advantages is, now suppose you decided to do this action, then you will actually do this action and the world will tell you which branch happened. You understand what I'm saying? So it would say, okay, you will actually get, let's say, Z1 as the observation. Then you actually are right here. So then you put B1 at the top and then expand further again to see which direction to go. If when you did the actual action you got this, then you have to expand B2. Okay. So this is sort of like, this is your online decision making for complex. Any questions? Yes?
I have a couple. So the picture seems to separate the, I guess, objects into three classes. We have belief states, and we have actions, and then we have this sensing action, which
These
is
are
somewhat
observations.
different.
They're observations. You missed two classes. You need to make up for them. So observations essentially are, it's one of the three pieces of the PalmDB. And in the case of observations, there is a certain number, a finite set of observations. Okay, and all you have as part of the PalmDB model is the probability that you will get this observation if you are in this state.
Yeah.
That's all you are given.
So, so if we have, for example, 3 observations, then the breadth of each would be 3.
Mm-hmm.
In this case.
Yeah.
Some
I mean, this is the smallest PalmDB you can get. 2 actions.
Yeah.
I mean, the other one is even worse, right? It's 1 action, and so there's nothing to do. Okay, 1 action, 1 observation is useless. So 2 actions, 2 observations is the smallest, and that's how it looks. Yes, go ahead.
Depending on the goal, not all observations are necessarily equal.
Meaning what?
So if my goal is to get to the copy machine, then an observation as to whether or not it's sunny or rainy outside is irrelevant with respect to any plan that I could come up with to get to the copy machine.
So in the PalmDB model, essentially, the standard PalmDB model, observations just happen spontaneously.
So you don't have a separate
You
action
don't have a
set of
separate
service.
let me do observation. That's the standard model. So the world we live in, we actually decide whether to observe, and observation has cost. And that's where you have to talk about value of information. The standard PalmDB model, which is as bad as it looks, it essentially is assuming that when you are in the state, you get the observation from that state.
So when you
And
check-
furthermore, you also are essentially saying you only get 1 observation in each belief state. So somehow that is sort of a partition function. So it's sort of the Z1 is, if you actually think the observations that you really get is it sunny outside or not, is it hot outside or not, and am I feeling tired or not, then it's giving you a number which is in the cross product of those valuations.
And the determination as to whether or not the observation is relevant depends on the probabilities of the respective belief states that we get into.
In this particular case, you don't actually, as I said, I think that the relevance to the goal depends only on the heuristic valuations here,
Okay.
ultimately. Okay? This is again, the best way to think about this is like game trees. Okay, relevance to a move depends on whether the leaf position is going to get you to a winning position faster. Okay? Other questions? Okay, so there is one variation, this is actually what you really need to understand. One other interesting thing is if you're doing online processing, then one thing is if you figured out, if you're executing then when you execute, so when you go down, then if you go down further, let's say, okay, so suppose right now there is an upper and lower bound for B1 in this tree. Okay, and there is an upper and lower bound for B2. Now suppose you actually got into B2. Then you will expand B2 further. Then you get a better upper and lower bound for B2. You can store these. And in fact, what the idea of RTDP actually is that every state has its value stored in a hash table. If the entry for that state, every belief state actually has its value stored in a hash table. Okay? And if that entry is null, then you quickly call the heuristic to compute the value to put in. If not, you take what's in the hash table. And whenever you compute a new value for a particular belief state, you put it in the hash table. This is kind of called learning. So this whole online search is also called, online decision making is also related to real-time search. And things like real-time A-star search and so on. And there is a version of real-time A-star search called learning real-time A-star search, where you essentially compute the backed up values, you remember the backed up values, so that next time around when you see that state, you have a better estimate of its value function than just what is given by the heuristic. Okay, if you do that, then presumably you can actually improve your performance. So if you are in this la la land where you are wondering, this is just online decision making, can I somehow find some kind of a mathematical theorem that says that this online decision making will compute a policy which will be optimal asymptotically? At least if I'm living, let's say, in an ergodic world where I don't die, and I keep doing this large number of times, over a period of time, could you have computed? Could I have reached a point where I would be starting to do optimal decision making? Well, yes, if you remember all the intermediate values you computed, then yes. Now, this is normally not a big deal, because if you have S states, you need a hash function of size S, a hash table of size S. Now, we have how many states? We have our hash function, hash table is in terms of belief states. There are infinite number of belief states, and it's very hard to malloc, an infinite sized hash table, right? So what do you do? What you do is you discretize the belief states. And then basically for each belief distribution, you can say discretize it into, let's say, 1 by n grid. Okay? And then basically you would then, so essentially that basically means 1 by n, 2 by n, etc., n by n are the quanta. And if I have a particular belief probability, I will see which of these numbers is it closest to, and I assume that is the bit for that. And then I only just assume that all those states are equally good, which is sort of kind of bosoness, right? Because I did this just for my happiness, and my discretization is fixed. Discretization. I didn't look at anything about the value function of the word to decide. Okay. So for example, if you discretize it in such a way, if you do it this way, then suppose you have a very sharp peaked mountain, right? The peak of the mountain will also be next to like big gorges, right? And so all of them will be in some sort of a, the probability that you are in this versus in that may be close enough that you are essentially giving the same valuation for slightly being off the peak, which means you're dead, versus on the peak. Okay, but barring that, essentially once you do the belief state discretization, you can get a finite sized hash table and you can keep track of the value functions that you're computing. Okay, updating it, and that's basically what is being done here. Okay, the way this algorithm is written, in some sense, if you are anyway remembering and improving your, so this RTDP does not even actually do any depth look ahead. Because the way this algorithm is written, anytime you are in a particular place, you just use the Bellman equation. Assume all the neighbors have their correct value functions. Using the Bellman equation, just figure out what's the best action to do. Okay, now that's obviously, given that, in the beginning stages, that's going to basically be very, very bad. But asymptotic convergence is not going to change. Okay, you can combine this with this by essentially combining a fixed depth look ahead or some finite look ahead with learning. Okay, in fact, I was surprised to find myself, I've always assumed, without looking into the papers, specific papers on RTDP, that RTDP doesn't actually have depth look ahead as part of it. Okay, to me it makes sense to just do both, but that's the way RTDP works. It doesn't do depth look ahead. It just assumes that the value functions are being estimated slightly, slowly as you live. Now, in fact, for this any type of real-time search to actually converge, the world has to be ergodic. That means you will be able to reach any state from any state, which means there is no depth. Okay, and then in which case you can compute that. Okay. Any questions?
Yeah.
Yeah.
On the previous slide, the picture here is this will work for either deterministic or non-deterministic actions, right? Or even stochastic. Yeah.
No, this is, yeah, obviously if you have, yes, yeah, basically, it doesn't matter. This is the most general case.
It'll just be the
In fact, it will be worth looking at this, staring at this and seeing what happens for deterministic, fully observable, stochastic, fully observable, stochastic, partially observable. This is the stochastic, partially observable case. Okay, and what also happens if it is a stochastic or deterministic, non-observable? In the case of non-observable, essentially there is no AND branches, there are only OR branches. You don't get any observations. Okay, so that is almost, so non-observable stochastic planning looks suspiciously like the pictures we used to draw for deterministic planning, because both of them will be R graphs. Except the space on which the R graph is drawn. In one case it's over space of states, in another case it's over space of belief states. Okay. Other questions? Yes?
So you mentioned that using this kind of hashing mechanism is difficult because you have an infinite number of belief states. That's because each belief state isn't just the set of states we think we're in, but also the entire history of how we got there.
No, but basically it's a probability distribution. A belief state is a distribution over these states. So basically any set of positive real numbers that add up to 1 is a belief state for these 3 state space. That's why it's infinite. Yes?
Has anyone tried just remembering the exact belief state and value comparison that were previously computed and taking combination of nearest neighbors?
I'm not quite sure. If you have
because they're a distribution over the actual states, it seems like you could take a linear combination of the nearest neighbors that were previously computed to get an approximation.
in some sense, when you discretize, that's what you're getting as like a side effect, because nearby states all get mapped to the same belief state, same quantized belief state. Okay. Let me just say that this entire semester, probably the topic that I probably am closest to not knowing what I'm talking about is this. Okay, so you should probably, there's a lot more that happens in PalmDB. That's why I gave you this, this overview paper. Okay, but some parts are true. Basically, eventually the complexity of the problem is just so darn high that about the only way you can do any progress is to just sort of hope that you're not in PalmDB world. Okay, or just take very small size PalmDBs. Okay, but the model itself is actually quite interesting. The model itself is quite interesting because it generalizes everything we have done up until now. So in fact, when we start doing reinforcement learning, which I might as well start next class, and you get to read the